today we have the pleasure to welcome Nikunj Saunshi from Princeton University, Department of Computer Science, working on machine learning and machine learning solutions that are grounded in mathematical principles and perhaps specifically in theory for representation learning and self-supervised learning. So Nikunj is supervised by Sanjeeva Arora, and the group has of course published several groundbreaking works in the field of theoretical analysis of machine learning and specifically deep learning. So today's topic will be theory for self-supervised learning. And welcome here, Nikunj, and the floor is yours.
Thank you, Olaf, for the invitation and the kind introduction. And good afternoon to everyone, and thank you for coming to this talk. So as Olaf mentioned, I will be talking about a couple of our works on developing some theory for self-supervised learning, more specifically for contrastive learning and language modeling. And I'll describe both of the settings in the due course of the talk. I'd just like to mention that feel free to stop me at any point for questions. I'll also be taking a few pauses in between the talk to answer questions, but feel free to stop me at any point or even type up the questions in the chat. Okay, yeah, so I'll start. So just for context, as we are all aware that supervised learning has been quite successful, especially in the last decade or so since the advent of deep learning, where you can just take a training data set. Let's say you have a labeled data set of dog and cat images, and you can use it to train the weights of a model of a neural network, more specifically, using some gradient descent like algorithm, and you can solve this task pretty well. So you can learn a model that can then learn to classify unseen or new dog and cat images, which is quite incredible in itself. Yeah, the success only got better once you increase the size of the data set and use the larger models. And I started using larger models, and with all the engineering development that happened along with it, enabled learning models that could even achieve performances close to that of human level performance. Of course, the strategies to increase the size of the model are better than what I described in this slide. So while this success has been incredible, it is a commonly known problem that labeled data can be expensive to obtain often, especially in cases where you require human annotators to explicitly label the inputs for the training data set. On the other hand, unlabeled data is quite cheap to obtain and in fact is available in abundance. So there's no dearth of text or images on the internet, for example. And it would be amazing if we could start leveraging the machinery that has been developed for supervised learning and use it in conjunction with unlabeled data to solve tasks well, because that's much cheaper to obtain. And in fact, this is exactly what self-supervised learning does. So it has emerged as a dominant paradigm to be able to leverage unlabeled data in addition to the techniques that have been developed for supervised learning and deep learning in general. And the idea is quite simple to describe. Basically, you would like to use the unlabeled data to construct certain pretext tasks or to construct some pseudo labels out of the unlabeled data. And now you can inherit the mechanism that was machinery that was developed for supervised learning to learn good models. And hopefully these models are also useful to solve the supervised learning tasks or the downstream tasks of interest. So very briefly describe the, I guess, the standard pipeline for self-supervised learning. So in the first stage, you would pre-train a model, or you would basically learn the weights of a neural network architecture of choice on the self-supervised learning task or the SSL task that has been constructed using unlabeled data. And the task that you construct is also an algorithmic choice in some sense. And once you have such a pre-trained model, you can use it to solve a downstream task of interest in one of many ways. So you can either use it as an initialization for a model that can then be fine-tuned by using the labeled data that is further available for that downstream task, Or you can do something simpler where you can extract features or representations from the pre-trained neural network and then learn a simple classifier on top of these fixed representations, again, using the label data that is available. So here by features or representations, one can think of using the output of the neural network at the second last layer, penultimate layer, or any intermediate layer for that matter. And besides these approaches, there are other innovative and task-specific ways of using the pre-trained model. In this talk, however, I would be focusing on this particular simple mechanism of extracting features and learning a simple classifier. And in fact, the simple classifier on top of the features would be a linear classifier. And this paradigm is also known as representation learning. And while it's simpler than, let's say, fine-tuning, using fixed representations actually still does pretty well in practice for various domains. And in fact, in some domains, it can even achieve performances close to that of supervised learning. And perhaps the main advantage of doing self-supervised learning using unlabeled data is that the pre-trained or the learned model requires very little label data compared to, let's say, solving the task from scratch. So this is intuitively, it's because you don't need to learn all of the parameters of the neural network now using labeled data. You're learning a lot of it using unlabeled data and only learning a simple classifier using the labeled data. So this is one of the main benefits of doing self-supervised learning. So just to give you a sense of what some of these methods look like, I'll just describe a few, let's say, ideas. Of course, this is a non-exhaustive list, but it's just meant to be a slice of the kind of methods that exist in the literature. So a very popular method is that of contrastive learning, where unlabeled data is used to construct pairs of similar points. And then the goal is to learn a model that can assign similar representations to the pair of similar points compared to, let's say, a pair of randomly selected points. So just to give some example, in the case of vision, a simple strategy could be to use two patches, two, let's say, small square patches within the same image as the pair of similar points. Whereas using the patch from a randomly selected another image as the random point. In text, for example, one strategy that has been used is to use consecutive sentences in a large text corpus as similar points. So if you imagine, let's say, a large text corpus like all of Wikipedia, for example, it is more believable that consecutive sentences in this are likely to be more semantically similar. So it makes sense to assign similar representations to these similar points. Another kind of method is that of input reconstruction, where you again just use the unlabeled data and set up this task where you want to predict part of an input given the rest of the input. So you're trying to reconstruct some features in some sense. And examples of these could be to try to use a black and white version of an image to reconstruct, let's say, the color channels of the image. Or in text, a very simple but effective strategy is to predict missing words in a sentence. So you just mask away a certain words in a sentence, and then you use the rest of the sentence to try to predict what would fill in those blanks. And another kind of work another kind of method is that of autoregressive language modeling. So I'm just going to restrict it to text, although some of these methods can also be used. Autoregressive modeling can also be used for other domains like images as well. In text, however, autoregressive language models use unlabeled data to try to set up this task where you can predict the next word given a partial sentence or given a context or history. So unlike reconstructing part of an input, you're trying to predict what word can appear after a sentence. So it's trying to predict what the future would be in some sense. And as I said, this is just a non-exhaustive list, a small subset of the kind of methods that exist in self-supervised learning. And in all of these, the learned model can be used to extract useful features. And in fact, you can just, on top of these features, you can just learn a simple linear classifier often where this linear classifier will be learned using labeled data. And then you can solve the downstream task pretty well. And an interesting question that arises is, why is it the case that solving the SSL task, referred to as task A, learn good representations for the downstream task, task B? And this is the fundamental question that would be the focus of the rest of the talk.
Nikunj, can I ask a question?
Yes, sure.
So I have a bit of a hard time distinguishing this sort of the formal difference between the sort of the autoregressive language modeling paradigm that you're outlining in the end, and then the masked sort of the missing filling in the missing word, sort of from a formal point of view. Can you sort of outline what the difference is here? So you have a missing word that you're predicting, and in one case you just seem to have a different context than in the other case.
Yes, so you're right in that these methods can be viewed as being very, very similar in that just the context that you have changes. So in the case of masked language modeling, you would let's say take a sentence and hide away 10% of the words, for example, and then you can learn a model that looks at 90% of the rest of the 90% of the words and try to predict what the missing words were in the middle. Whereas with autoregressive models, instead of doing this, you can take an entire sentence and you know what the next word is that appeared in the text corpus. So you can try to predict what the next word was. And it doesn't have to be a full sentence. Let's say you can look at every small chunk of a partial sentence and try to solve this task. And one fundamental difference between the two would be that with autoregressive model is a complete generative model. So it's modeling the entire, it can be used to model the entire distribution of text, because you can factorize any distribution. You can factorize the distribution of the entire corpus as this product of conditional distributions, where you're predicting the ith word given everything before the ith word. So you can, in principle, use it as a generative model for text, whereas the masked language model is not a complete generative model, because you cannot completely model the distribution if you just predict some 10% of the missing words, let's say.
Okay, so the main difference here is that one is intrinsically generative because you factorize a joint distribution. The other one, you build some sort of pseudo likelihood, right, of the joint distribution, right?
Yes, that's correct. So in some sense, the masked language modeling objective is trying to learn like some subset of the, not subset, but like some part of the entire distribution.
Okay, thanks a lot.
Yeah. So in this talk, I am viewing autoregressive language model more as a self-supervised learning task. Like I'm treating it as a pretext task that you construct. But yeah, I think the fundamental difference is this. Yeah, thanks for that question. Okay, so I'll move forward. Yeah, so as I said, the main question that we are interested in is, why is it the case that solving the SSL task can help solve seemingly unrelated downstream tasks with very little labeled data? So I didn't describe earlier, but in the previous slide, but the downstream tasks could be, for example, in the case of images, after whatever self-supervised learning task you solve, you can use the model to classify images into different object classes like dogs, cats, automobiles, etc. And similarly for text, you can have multiple different downstream tasks that I'll describe at a later point. And this actually raises a more general and interesting question of why is it the case that solving a task, any kind of task A, helps with a different kind of task B? And more specifically, why does solving A help solve B with very little data? And if you think about this, it's actually not a very ambitious property in the sense that we already know that humans do this kind of transfer. So humans can solve a particular task and transfer the knowledge and skills that you gain in while solving the task to solve different tasks. For example, the skills of, let's say, balancing that you learn while learning to ride a bicycle is certainly helpful when you then try to learn to ride a motorcycle, let's say. Or getting a math degree can also be useful. For example, the deduction skills some kind of deduction skills that you learn while in the course of getting a math degree can certainly be useful to do well later in law school as well. And perhaps a more classic example that I like to use is from the Hollywood movie, The Karate Kid. So in this movie, the protagonist wishes to learn karate. However, to his frustration, his karate teacher does not really teach him any karate moves in the first, I think the first few months. Instead, he asks him to do really basic chores like painting the fence or scrubbing the floor. And this really frustrates the protagonist. However, it turns out that some of the basic motions involved in doing some of these basic chores, so practicing these ended up helping him learn karate moves much more easily. And of course, yeah, he was happy at the end. I'll try not to spoil much more of the movie, but this is the gist of it. And in fact, the first stage of, let's say in this case, doing chores did not really require any explicit supervision. So it was in some sense easier to teach the protagonist to do so. And this is probably the setting that's closest to self-supervised learning in some sense, where in the first stage, you just use unlabeled data, and then the model helps you with downstream tasks that do require labels. So given that this seems like an interesting property, and certainly it seems like a property that we would like to infuse into our machine learning or artificial intelligent agents, this does raise a theoretical challenge, which is what are the mathematical principles that can help us understand why solving a particular task A can help with solving another task B with little label data. And just to reiterate, lately this has been quite a dominant paradigm, or there have been quite a few successful methods that employ the strategy of self-supervised learning. And while there's a rich line of literature that that has been developed for supervised learning, most existing frameworks somehow do not capture all the aspects that one would like in order to understand the success of self-supervised learning. So one of the biggest differences from supervised learning, of course, is that there's a huge shift in potentially distribution and also the loss function between the two tasks at hand. And we'll see in the examples of contrastive learning and language modeling how these are different. And furthermore, unlike the setting of semi-supervised learning that you might be familiar with, the standard approach of using self-supervised learning is to not use any label data in the first phase. So it's almost as if you don't have access to any label data, and you're just constructing tasks using unlabeled data. And furthermore, we would like to extend it to settings where we can adapt to the deep learning pipeline that is actually being used in practice, and that has led to this success, rather than using simple models like, let's say, linear functions, for which developing theory is sometimes easier. And in this talk, I will be focusing on two types of methods, as I said earlier, contrastive learning and language modeling. I should point out that unsupervised learning is also a terminology that has been around, and it's kind of similar, where you still want to use unlabeled data and learn a useful model. Or sometimes you just want to learn, you want to do some data analysis like clustering, etc. There has been this separation that has been made in the literature, where self-supervised learning methods are the ones where you kind of construct a task out of unlabeled data and then try to solve it. And in some sense, the existing frameworks for unsupervised learning also don't completely capture all the aspects that we would be interested in. So yeah, so with this basic background, I'll just pause here for some time to see if there are any questions about the setting.
Yes, Sepidin.
Hello, I have a question. I have seen some works that they use some sort of pseudo labeling. Do you consider those as a self-supervised learning as well? Like, for example, they train a model based on the labeled data, and then they use that labeled model for pseudo labeling in the next steps, or some sort of learning the representation later on.
Right. So I guess maybe you can correct me if I'm wrong. So in this case, you do have access to some label data, and then you would try to learn a model on this small subset of labeled data. But then you use the model that you learned to label, let's say, the huge pool of unlabeled data that you have. And then you treat them as pseudo labels and add that to your training set and then learn a model. Yes. So I think this wouldn't really be technically considered as a self-supervised learning approach, because, as I said, the standard assumption is that you don't really have any labeled data at the start. On the other hand, I don't want to make any sweeping judgments on the definition of self-supervised learning, because I think maybe some people might use it slightly differently than others. So just to be safe, I'll also state that. But yeah, the way I view it is just having unlabeled data in the first phase. So you have no idea of like really what really your downstream task could be. Maybe you have some sense of what it could be, and that's what you try to exploit in the construction of this pretext task. And I'll show examples of what it means in contrastive learning.
Thank you.
Yeah, thanks for the question. Okay, so yeah, so with this basic setup, I'll move forward and I'll describe our work on theoretical analysis for contrastive learning. And this was joint work with many of us at Princeton and our advisor, Sanjeev Arora. Misha Khodak was at CMU at the time of this work. And this was published at ICML 2019. Okay, so I briefly touched upon this point, but I'll describe contrastive learning in more detail. So as I said earlier, in contrastive learning, you would like to use the unlabeled data to construct certain pairs of similar points. So the pairs of similar points is denoted as x and x plus here. So for any given point x, you use a similar point x plus. Sorry. And then the task that you set up is to try to learn a representation function f, such that the representations assigned to this pair of similar point x and x plus is high. And you want this inner product to be higher than, let's say, the inner product of pairs of points x and x minus, where x minus could be picked, could be a random point, or in the literature, it's also denoted as a negative sample. So you want similar pairs to have higher inner products than, let's say, the point and the negative sample. And this representation function f can be parameterized, can be a parameterized function. Let's say it could be a neural network architecture of choice, where you use, you get rid of the final linear softmax layer that you typically have and just have the representation layer as the output. And this idea can, so one of the, I guess, prototypical objective function that tries to achieve this looks like the following, where you have an expectation over a distribution of pairs of points x and x plus and a negative sample x minus, in this case, just one negative sample. And you have this logistic kind of loss, where you can see that if you like trying to minimize this loss function on the representation function f, will kind of guarantee the properties that I described earlier. So note that there are, of course, many variants of this objective function, including ones with that use multiple negative samples, and they work with various degrees of success on various data sets. But this is this simple objective function is enough to drive through the point that I want to make. So just to give some examples of what the similar pairs x and x plus can look like. So one of the earlier approaches for images used successive frames in a video as similar points, because they're likely to be more similar in some sense. And another approach for text use the strategy of using consecutive sentences in the text corpus as similar points, since they're likely to be more semantically similar. And in fact, after our work on analysis of contrastive learning, there have been a bunch of work, and I should point out that these have come up independently. So it's not really it's like independently there has been a line of work that has used contrastive learning for images, where similar points are used. For similar points, you use two augmentations or two modifications of one image as augmentations. So examples could be using random crops within the image as these augmentations, or applying some Gaussian filter on top of the image and applying some random levels of Gaussian blurring or grayscaleness to the image and things like that. And these kind of approaches actually were the ones that perhaps SimClear was one of the approaches that really got the performance of self-supervised learning close to supervised learning in the domain of images. So once you learn such a representation function f, let's say for images, you can then use it to solve a downstream task by first embedding all of your labeled data that you have, let's say, for the downstream task into this vector space using the representation function f. And then you would just use the labels to learn the simple linear classifier that separates the vectors or the representations that you have. Similarly, for text, a typical downstream task might be, let's say, that of sentence classification, or at least one of the simple tasks is this. And for, let's say, the task of classifying movie reviews as a positive or negative sentiment, you can do the same strategy. You can embed all sentences in the downstream task or all movie reviews using the representation function and then learn the linear classifier. So this is the basic setup that we would be interested in. And the precise theoretical question that comes out of this is, so since we are learning a representation function by trying to minimize the contrastive loss, why is it the case that a function f that has a small value for the contrastive loss should do well on downstream tasks? So a priori, again, the similar pairs that you have do not seem directly connected with the downstream task. And this is a valid question to ask. That's why does this happen? And the key idea that we leverage in understanding contrastive learning is that the similarity distribution or the distribution over similar pairs x and x plus somehow implicitly encodes the downstream label information. So although you don't explicitly have the labels, the information about the downstream labels and classes are somehow encoded implicitly through this similarity distribution.
So can I ask a question at this point?
Sure.
So do you implicitly assume already here that there is some notion of similarity between x prime given to you beforehand? Did you design this given to you beforehand, or?
Yes. So as I guess I was describing in the previous slide, usually this you would construct these pairs of similar points using unlabeled data. Let's say using some prior knowledge about the domain and just some human knowledge of what you think could be similar pairs of points. So for text, you could use like consecutive sentences in the text corpus, which is quite easily available, and treat them as a similar pair.
But for your theory, you assume there is some similarity function with some properties.
Yes. So in theory, yeah, we make assumptions about what kind of props. So the goal, I guess, is to understand what kind of properties for the similarity distribution, what kind of assumptions can lead to some kind of can lead to an analysis that can show the benefit of learning a representation through contrastive learning like this. So it's an implicit assumption about the generative process, let's say, which is kind of, I guess, in like there's a lot of like theory that kind of uses this approach. Yeah.
I mean, for example, could you use a well-known domain kernel for that particular application?
Yes, you could use a domain kernel as one of the examples. Although if you use a kernel, so if you use a kernel, in some sense, the problem becomes much more well defined, but sometimes it's unclear whether you can do any better than the original kernel that you start off with. So there is some kind of trade-off, I guess, in that sense. But most of the standard approaches that actually end up working well in practice use this heuristically constructed approaches of just using pairs that kind of make sense that they're similar. You could infuse in like some kind of domain knowledge in the form of some kernels as a similarity function as well. And in fact, I should point out that there is an even older line of work that actually tries to understand, let's say, similarity functions that are based on kernels, roughly based on kernels, and how to learn like using this kind of a similarity function as well. So maybe if you're interested, I can point you in that direction. Offline.
Thanks.
Yeah. Okay. Yeah. So as I was saying, so this is the key idea that we want to exploit. So this is the kind of assumption that we want to make. And more precisely in this work, the formalization of this idea was that the pairs of points x and x plus are somewhat conditionally independent given the downstream labels. So given some kind of latent classes, So I say latent because these classes, as I said, are not really visible to you, so you don't get access to those. But there is some latent classes that governs the generative process of the similar points that we assume, and the pairs of points x and x plus are assumed to be conditionally independent given that generative process. And of course, this assumption is not going to be exactly satisfied in practice. But as I was saying earlier, like the goal is to try to see what kind of properties can enable us to do some kind of theoretical analysis. And using this formalization, we could show a result that looks like the following: that the contrastive loss for any representation function f is kind of a surrogate loss for the classification loss of this representation function f. So under this assumption, you can show such a result. So I won't go into detail of how this classification loss is defined. Roughly, it's just some kind of average binary class. You can take a randomly sampled binary classification task and learn the best linear classifier on top of the representation and evaluate the loss on that. And what we can say is that I guess in the big O notation, you can say that the classification loss of the representation function f is of the order of the contrastive loss. And now we can see why minimizing the contrastive loss makes sense, because it is in fact some kind of a surrogate to the classification loss. So it is desirable to learn representations with small contrastive loss. So this is just like a rough idea of what the result looks like and what the theoretical assumptions look like. Maybe just to delve a bit more into the specific result. So as I was saying earlier, this term L classification of f can be thought of as the classification error of after you learn the best linear separator or linear classifier on top of the fixed representation function f. So this is the quantity that is being upper bounded. And note that the contrastive loss can be made quite small or smaller. Rather, I should say that the contrastive loss can be made smaller since you have a lot more unlabeled data at hand. So there's no real issue of sample complexity in being able to make the contrastive loss small, because you can almost assume that you have access to a lot of unlabeled data in principle. And the main benefit of self-supervised learning in this case is the following. So firstly, this result shows that the representation function f learned that has small contrastive loss is at least expressive enough to be able to classify the classes of interest. And furthermore, these representations are going to be low dimensional. So since we're only learning a linear classifier in this low dimensional representation space, this actually requires not a lot of label data compared to, let's say, learning the representation function, which was a neural network, from scratch using just label data. So that would require many more samples than, let's say, learning a linear separator in low dimensions. And this is how you can see the benefit of self-supervised learning in this setting, how it reduces the downstream sample complexity. So I'll just pause here to see if there are any questions about
can I ask one?
The result. Yeah, sure.
How do you assess the goodness of task 2 in classification? For example, once you have this plane and you know you can separate the two classes, I guess you can't name them dog and cat because you just know they're class 1 and class 2. Mm-hmm. And do you use labeled data, or do you have another way of assessing the goodness?
Yes, so it's a good question. So this classification loss that I defined here is using access to label data in some sense. Once you embed these points into this vector space, so hopefully you can see the mouse pointer, right? Otherwise, I'm just moving it.
Yes, we see it.
Okay, good. Thanks. So once you embed these points into the vector space, this linear classifier, this green hyperplane that is learned using the label data, as you were saying. So that you know what different points mean. Like, you know, this class means dog and this class means cat, for example. So yeah, this quantity on the left-hand side is actually after using the label data.
Maybe did the person get an answer to the question? Otherwise, I'll ask another one.
Oh yeah, sure. I assumed it was answered. Thank you.
Okay, so for me, I'm just trying to understand a bit sort of it seems it seems very heuristic, right? And I think you are very transparent about the sort of heuristic nature of this approach. And I guess the point is that you want to bring some transparency to it, but wouldn't a good experiment be to sort of look at some very controlled, like for instance, symmetry groups, like, and then try to see if you approximate closeness in those spaces on transformations of sort of very geometrical objects or something like this, to see whether you actually learn meaningful distances with losses like this? Is this something that has been explored?
Okay, so
very off topic, sorry.
No, I think it's a good and possibly a very relevant question. So maybe I should point out that like when we were working on this, just as before completely answering the question, when we were working on this, somehow contrastive learning and especially the more recent approaches that have been more successful weren't really out. So the more recent approaches actually do use some kind of data augmentation, if you're familiar with it, and some kind of transformations, and perhaps you were alluding to those kind of transformations. And so the result here was motivated a lot by the examples from text, where let's say consecutive sentences were used as similar pairs, where it's kind of more believable, I guess, that some such assumption might hold, even though not exactly this. Of course, theoretical assumptions never hold in practice. So we just hope that the analysis turns out to be useful. But I do agree that the more recent data augmentation approaches actually require perhaps a slightly, or maybe a more different way of looking at this problem. And there have been recent work, at least one or two recent works that I'm aware of, that try to understand this with like weaker assumptions in some sense on the similarity distribution, and they align better with the data augmentation kind of maybe similar pairs, and this kind of might, where possibly you can exploit the symmetries that you were referring to, or let me know if I understand, didn't understand the question well. And actually, so there is also, so currently I'm also working on trying to in fact incorporate even other aspects of that could affect why self-supervised learning works well, and not just like notions of assumptions on the distributions that have been made, for example. So maybe on the function class being used and things like that. So there is a lot, I guess there's a lot more to explore here. And this is probably just scratching the surface and like just the initial stages. There's a lot more to explore here.
Yeah, thanks a lot. I think you sort of got the gist of my question. I think the basic point I tried to make was basically whether you, for instance, if you do a translation or something like this, like only do translations as augmentations, or whether you learn something that is related to the translation group, or if you do like 2D rotations, whether you learn something which is related to the distances or notions of distance in the SO2 group, right? So that was my point here, but thanks a lot.
Yeah, no, I think yeah, all of that makes a lot of sense, and I don't think that there is any specific analysis that I can, or at least I can think of, or I have come across, that like specifically looks at particular groups of interest. It's been more abstract in terms of assumptions about distributions and things like that. Yeah, thanks for that question. It was a good one. Okay, so this is basically what I'm going to be presenting for contrastive learning, and I do have the link to the paper at the end. So if you're interested in knowing more or chatting more about it, I'll be happy to do it offline. Oops. So yeah, so this was the results from our work, and I just again want to point out I guess the most important takeaway from what I presented earlier is, besides the so I think the more important component here is actually the key idea and how that has been formalized into an assumption and things like that. Because once you have the mathematical assumption, I think showing that kind of result is, especially the one that we showed, was not very tricky or not very difficult. I think the main contribution, I guess, was the idea that the similarity distribution somehow implicitly encodes the downstream label information. And so this kind of idea was also used in some follow-up works, including some from our group and some with me on them, but also including some other works, quite interesting works actually, that kind of try to build upon this idea and make weaker assumptions about how the labeled information is encoded in the similarity distribution, and then how you can still show guarantees and somehow make the analysis closer to what's happening in practice. Although I would say that this is still insufficient to completely explain what's happening in practice. So this is still like a open and an active area of research. There are other kind of approaches or analysis that try to explain the success of contrastive learning. But I guess in the interest of time, I won't really describe them, but I just have a couple of citations and I can point you to more papers if one is interested. Okay, so now I'll move on from contrastive learning and I'll describe this other work that deals with language models, more specifically autoregressive language models, and how can we understand why they help with downstream tasks. So this is joint work with Sadika Maladi and our advisor Sanjeev Arora, and was published at iClear 2020. So just to describe the problem of language modeling once again, in very simple words, the way I'm going to view language models or autoregressive language models are as next word predictors. So for any given context or a sentence S, a goal of a language model is to predict what the next word is. So suppose I have this context, I went to the cafe and ordered a language model will try to predict what the word would be that can follow this context S. And it does so by outputting a distribution over words. Sorry. So I'll denote this distribution as P sub S. And the hope is that the language model outputs a distribution P sub S for the context S, such that it assigns high probabilities to words like latte or bagel that can potentially follow this given sentence, but very low or almost zero probability to words like dolphin that likely and hopefully won't follow this context S. And again, so this, as is typical in deep learning, this language model is parameterized by some kind of neural network architecture of choice. And the weights of it are learned by using data, using unlabeled data that is constructed from a huge text corpus. So you can think of all of Wikipedia, let's say, as a text corpus. And using this unlabeled data, you can generate pairs of S, W, where, for example, you can just take any partial sentence S from the text corpus and use the word after it as W. So you can like very easily generate these pairs. And given this, you can try to learn the weights of the model by minimizing the following cross entropy objective, which is the most standard objective. So this objective is an expectation over the pairs of S and W from the text corpus. And it tries to minimize the negative log probability that the model assigns to the given word W that follows a context S. So it's trying to maximize the probability assigned for pairs of S and W that are observed in the corpus. And equipped with the simple strategy. So the simple strategy of using unlabeled data and training a model with cross entropy loss. Actually, language models learned in such ways ended up being, turned out to be quite useful to solve downstream text classification tasks. So they could be used as initializations to fine tune from to solve these text classification tasks. And in fact, with the improvements in model architecture, that is using the transformer architecture in place of a recurrent neural network and using a much larger model, actually these language models learned could solve a bunch of downstream tasks and not just text classification. So they could be used to solve tasks like text generation, question answering, machine translation, and again, sentence classification. So it could solve many more tasks. And in fact, with an even larger model and even larger set of authors, you could do even better. So you could now solve these tasks, not only solve these downstream tasks, but you can solve them with very little labeled data. So also what is referred to as a few shot learning setup. And it's quite interesting that this very simple strategy of just minimizing cross entropy objective using these pairs of S and W from unlabeled data can get you so much. And yeah, so we are quite interested in understanding how or like what principles can enable this kind of benefit. So again, just as earlier, just to ground the exact setup, in the first self-supervised learning stage, you would pre-train a language model on the next word prediction task using unlabeled data. And as I said earlier, you do so by minimizing this cross entropy loss. So the model that you're learning can be denoted by these distributions P sub S for now. And in the second stage, you can use the language model for downstream tasks. And again, you can do it in the same way. So now what we are going to do instead is take, let's say you had the task of sentiment classification of movie reviews. I'm just going to use the output probabilities for any given sentence that the language model outputs as the feature vector or representation for any given movie review. And again, using label data, you can learn the linear separator on top of it. And now the precise question that we want to understand is, why is it the case that learning a language model that has a small value for the cross entropy loss do well on downstream tasks? And in this case, we are going to be specifically looking at the downstream task of text classification or sentence classification for simplicity. And the key idea that we kind of try to exploit is that many classification tasks of interest on sentences can actually be rephrased as some kind of sentence completion problems. And I'll show later examples of how this can be done, and also experimental evidence for this. But if you once you believe me that this can happen, then one can see why actually solving this language modeling task that tries to predict the next word can actually help with a downstream classification task. And as before, as before, we can formalize this idea into a mathematical definition. Again, I won't go into details, but we define this notion of a natural classification task. So it is a task that can be solved through a sentence completion reformulation. And more precisely, it can kind of be solved as a linear classifier on top of P star of S. So P star of S here is the ground truth distribution of words that can follow any given context S. So note that in language, the next word is it's usually never going to be deterministic. There could be many different words that can follow, and this uncertainty can be captured through a distribution over words, and that is denoted as P star of S.
So sorry, just a clarification. When you say you can be solved with linear classification classifier on top of P star of S, you mean on top of the representation learned by this P star of S?
Okay. So sorry. Yeah, I should have mentioned that earlier. That's a good question. So you can view P star of S as a distribution that it is, but you can also treat it as a vector of probabilities. And if you use this vector of probabilities P star of S as the representations, that can, if you had the ground truth distribution, then you can like linearly classify your sentences, let's say. Does that answer the question?
Yeah, thanks.
Okay. Right. So in the paper, we also justify why this assumption of linear classifier on top of P star of X makes sense under a sentence completion reformulation kind of approach. But given this formalization, now we can actually show some kind of mathematical guarantees, which are again not too difficult to show once you have all of this set up. And what you can show is that if you have a language model P of S, that is a probability distributions that are epsilon optimal in the cross entropy loss. So in other words, the cross entropy loss that we are trying to minimize is close enough to the optimal cross entropy loss that can be achieved, and it's epsilon close to it. Then you can show that the classification loss of using the output probabilities from the learned language model can be upper bounded by a sum of two terms. So the first one, that is tau, will denote how natural the task is. So in other words, it will kind of denote, how well does the task kind of satisfy this kind of assumption, the sentence completion reformulation assumption. And the second term here is what you suffer because of the suboptimality of the language model. So in practice, you can never learn the optimal solution for numerous reasons, right? You only have a finite, even though you have a lot of unlabeled data, it's still a finite data set. So you're not really minimizing the loss on the distribution. Also, there are issues with the representation expressivity of your function class used, and also the fact that you're using a particular gradient descent algorithm and whatever algorithm that you're using and things like that. So you may never achieve the optimal solution. But if you do have something that's epsilon close to optimality, so if you can drive the cross entropy loss to be quite small, then you can end up getting better and better guarantees. So as epsilon goes down, you can get better guarantees, which is intuitive, but it can be mathematically captured like this. So again, this is like overview of what the kind of theoretical result does look like. And so as I said earlier, I won't go into the details of how to show this result and like all the nitty-gritties, but I would like to spend some more time on this idea of sentence completion reformulation and try to argue why that kind of makes sense for language. So for that, suppose let's consider a binary classification task on sentences. So suppose you have the sentiment classification of movie reviews. So the data set is you have movie reviews with a label of +1 or -1 based on whether it is a positive or a negative movie review. So to try to understand why language models can help solve this task, we first look at this thought experiment. So we know that the language models are trying to learn the ground truth distribution of words that can follow a given context test. So to understand why language models can help, it makes sense to first understand why even the optimal language model should be able to solve the downstream task. So suppose I had access to this, I had an oracle access to the ground truth distribution P star of S for every sentence S. So I have the distribution of words that can follow. So can that be used to solve the sentiment classification task? So consider, let's say, a movie review, which is, I would recommend this movie. And I know what is the distribution of words that can follow this. How can I use this to find the sentiment of this movie review? And if I give you enough time to think about it, I'm sure you'll come up with interesting strategies. And perhaps a very simple strategy is to just use the probability assigned to two words or two tokens, the smile and the sad emoticons. And you can see that it is more likely for a positive movie review to assign higher probability to the smile emoticon. So just using this simple comparison of probabilities can actually might give you a pretty good sense of the sentiment of the movie review. And in fact, this strategy can be rephrased and written as a linear classifier on top of the vector of probabilities P star of S. So if you have the coordinate, if you have +1 for the smile token and the -1 for the frown token and 0, let's say, in the other coordinates, this simple linear separator is equivalent to what the predictor is described earlier. In fact, you can do better with this strategy. So instead of just looking at the words that follow this movie review, I could add a prompt at the end of each movie review. Let's say a fixed prompt, this movie is blank. And now you can see that you can use the probabilities of a larger set of indicative adjectives like good, brilliant, or boring. And perhaps since different words correspond to sentiment or capture sentiment to different degrees, you could use a weighted combination of these probabilities and try to estimate the sentiment of this movie review. And in fact, this strategy of adding a prompt allows for being able to use a larger set of grammatically correct completions. So you're making better use of the distribution that you have. And it also helps extend this idea to other kind of classification tasks, like let's say topic classification. And overall, this exercise was just to try to motivate that it is somewhat believable that at least classification tasks, at least some of them of interest, can be rephrased as a sentence completion problem. And more precisely be solved by this linear classifier on top of a vector of probabilities. And in fact, we also try to kind of verify whether this kind of sentence completion reformulation strategy is beneficial in practice. So what we do is we take a pre-trained language model. So we use the GPT-2 language model that came out from the work in OpenAI. And we consider two data sets. One is SST, a sentiment classification data set on movie reviews, and the other one is AG News. So it's a topic classification data set on news articles. So what we do is for any of these tasks, we use the output probabilities from the language model and take some coordinates of it as features of the inputs, and then learn a linear classifier using labeled data. So for example, in the case of sentiment classification, so in this column, we do the following. So we look at the output distribution for any movie review from the language model and just pick out two coordinates, the smile and the frown emoticon, based on the strategy I described earlier. So now the feature vector or representation for every movie review is just two-dimensional. And then we just learn a two-dimensional linear classifier using the label data. And we can actually get pretty decent performance. So you can get up to 78 or 79% accuracy on this binary classification task where random guessing is around 50%. So you can do much better than random, but just using these two coordinates and probabilities of those two coordinates from the language model, which we found to be quite interesting. And in fact, if we did the strategy of using a larger set of indicative words, let's say adjectives that kind of make sense for sentiment, so good, great, boring, etc. So we just pick out those coordinates and the probabilities on those coordinates for every movie review and learn a linear classifier again, roughly just 30 words. So it's like a roughly 30-dimensional vector. You can actually get a much better performance. So you can get up to 85% accuracy. And just to clarify, this second row here is actually the case where we added a prompt at the end of each movie review before getting the output probabilities from the language model. And we see that actually adding the prompt does help. So this also is kind of in line with the sentence completion reformulation. You want to make the task more amenable, or like make the completions that you get more grammatically correct. And you can see similar trends for this topic classification task on news articles. So there are 4 topics: science, politics, business, and sports. And again, you can add a task specific prompt like this article is about at the end of each news article, and you can get pretty good accuracies on this. So just for some baseline comparisons, bag of words is a very traditional kind of baseline for text classification tasks. And you can see that you get numbers close, at least competitive or close enough, even though not right up there, maybe for the topic classification task. And in fact, if you actually do the more standard protocol of taking the pre-trained language model and fine-tuning it on the downstream task, you can actually get better numbers. So the strategy, while simple and while makes the point of the sentence completion reformulation, it's actually not entirely sufficient to reach this performance. Although in the paper, we have a more general result than the one that I presented earlier, which actually does not, instead of randomly select, or so instead of arbitrarily selecting some kind of 30 coordinates or 30 words of interest, you can do something more principled where you can use some kind of low dimensional projection of the output probabilities. Again, the low dimensional projection is also determined by the language model, and it naturally comes up in the theory. And those features actually do much better than this column. And they kind of at least help reduce the gap between like the fine-tuning procedure and this. So in some sense, like the features that somehow naturally showed up in theory ended up actually doing pretty decently in practice also, with just simple linear classification. Okay, yeah. So I guess in the interest of time, I won't go much into what, the other details of what we have in the paper. However, there is a lot more to explore here. Again, I think this is just scratching the surface in understanding language models and why they are helpful. And since they are becoming such a big driving force in NLP these days. So I think this is a very interesting and very relevant question. So as somebody pointed out earlier, mass language models are like an extension that would be very nice to somehow capture. So BERT-like models, if you've heard of them. And also going beyond this idea of sentence completion reformulation, like what else can a pre-trained language model capture apart from being able to complete sentences? What intermediate representations that it learn and things like that. And of course, what I described here was just for classification tasks, but there are a lot of other NLP downstream tasks of interest. So like, it would be interesting to see how some of these insights translate to some other tasks of interest. And just like as broad takeaways for like whatever I described in this talk. So again, so the main point that I guess I would wanted to take away is that it's just this key idea of trying to connect the self-supervised learning task to the downstream task. So what is this and how to so in the case of contrastive learning, for example, the connection was how the downstream label was implicitly encoded in the self-supervised learning task or the contrastive learning task itself. And in the case of language model, it was the case that the language modeling task or the SSL task of next word prediction somehow was a superset because the downstream task could be rephrased as this task. So that's perhaps why it was useful. And like understanding what are other key principles that can help us understand the benefit of self-supervised learning, I think is a very interesting question. And of course, then there is a step of like trying to formalize these ideas. So into some mathematical definition. So for example, in the case of contrastive learning, it was done through this notion of conditional independence of similar pairs of points given the downstream label. And as I said, these kind of assumptions have been weakened in subsequent works. In language modeling, the assumption was about this, the definition of, let's say, the natural task and how a sentence completion reformulation can help solve the downstream task with a linear classifier on top of the ground truth probabilities. And finally, just like a takeaway, like I think showing the results is it's nice to see, but I think the main ideas and the formalizations are, I think, quite useful and probably hopefully leads to something that actually we can see progress even made empirically, let's say, through insights obtained through this. Yeah, so I think overall, in order to understand self-supervised learning methods better, I think there is a lot of interest these days, and there are a bunch of high-level questions like what signal do these pre-trained models actually try to encode, and what kind of pretext tasks would be useful? So how to design these pretext tasks is another interesting question. And as I was saying in the previous slide, how to mathematically capture the benefit of self-supervised learning methods so that maybe through the language of math, hopefully we can like try to come up with improvements and things like that. And I think an interesting question also, which I did not touch upon in this talk, and it's because the results that I presented were mostly making assumptions on the distribution. But there's another very important component, which is the inductive bias of the model architecture that is used and maybe the training algorithm that is being used. And that somehow also affects what all the pre-trained models can learn. And I think this is a very interesting question for exploration. And I think some of these questions have kind of been touched upon by various kinds of works recently. So yeah, I think it's a very active and interesting line of research. Yeah, that's all I had to present. Thank you so much for listening in and asking questions. I'm happy to take more questions now, and feel free to send me an email for any follow-ups or discussions, etc. And I just have the links to the archive versions of the 2 papers that were described in this talk. Yeah, thank you.
Thank you, Nikunj. I think we can try to have a couple questions. So Alba is raising a hand.
Yes. Hi, can you hear me?
Hi, yes, I can.
Hi, thank you very much for a very nice talk. What I see is that you really try to make this connection between the choice of the self-supervised task and the downstream task. And do you have any tips because for contrastive learning and classification problems, it's kind of easy to know how you would choose the self-supervised task. But for example, if you have like image segmentation problems or like object detection or things like that, do you have any tips about how to choose this self-supervised task?
Right. So, I would preface the answer by saying that I don't know if I have any tips that go beyond, let's say, what actually people have tried in practice or that has been explored in the empirical literature. But maybe a very rough answer would be that actually it's kind of an intuitively obvious one. So some of the insights that we got out of this were that you would like to take transformations to the inputs, let's say in contrastive learning. You would like to use transformations that are, let's say, invariant to the label. So the label does not change with those transformations, but they somehow try to capture a lot more of the distribution. So they try to encompass, let's say, a diverse set of images in some sense, so that you can have more of this conditional independence like structure that you want, let's say, augmentations of images from the same class to actually be more similar to each other and things like that. So you want the augmentation distributions to be more similar. So like that's the rough intuition that comes out of theory. I'm not sure if this particularly says anything directly about what kind of changes that need to be made in practice, let's say. I don't think like the theory is at a mature enough state to be able to make those predictions yet. Although I guess it is interesting to point out that I found out like some follow-ups to this and also some independent papers that try to tweak the process in some ways. So there's this paper, De-biased contrastive learning, from a group at MIT that actually tried to, let's say, use the framework that we had and like tweak the process or tweak the contrastive learning objective slightly in a way that made sense from this theory. And actually that led to better performance or slightly better performance in practice. So I think, yeah, like those are the kinds of small insights maybe that exist, but I don't know if there's like something really big that comes out of the theory yet. But yeah, I'm hopeful.
So in a way, it's just a matter of trying to find a self-supervised task that will improve the result in a way.
Yes, I think there can be some intermediate tests that maybe that you can get out of these, let's say the theory for this. So I'm not very familiar with this work, but maybe if you're interested, I can point you to it. So there was also this some kind of pretext task selection that was done for speech recognition using insights from this conditional independence or approximate conditional independence that we had in a follow-up paper. So yeah, I'm not entirely sure of the details of it, but if you're interested, I can like point you to that paper. So that kind of tries to determine how to select tasks based on how much conditional independence like structure you have in the pretext task in some sense.
Yeah, sure. Then I'll write you and ask for the reference.
Okay, yeah, sure.
Thank you.
Yeah.
Nikunj, would you say that there may be some work that will sort of develop some more principled way of designing the pretext tasks?
Yes, I think I'm hopeful. Although I don't think it's going to be just theory saying that, oh, so I did a bunch of this math and this is exactly what we need to do. I think it's going to be a combination of like some kind of empirical exploration of maybe theory can serve as a guidance for these are the properties that are desirable, and like roughly we can check whether these properties hold in practice, and like, oh, this property holds. So yeah, maybe now I can try this out and see that this holds in practice and things like that. I think even in terms of theoretical understanding, I think it's still in a nascent enough stage that we haven't even captured all the aspects that lead to the success of self-supervised learning. So as I alluded to earlier, I think this inductive bias of function class and algorithms actually play a huge role in what the model learns, and more specifically what the model learns as intermediate representations. So most of what I described here was actually using the final representation that that is learned by the model in, let's say, any self-supervised task, and using the final representation for the downstream task. But in many cases, for example, the intermediate representations are better, and they capture some kind of, there's some hierarchical learning kind of things that happen that have been empirically observed in practice. So these kind of things have not yet been captured by theory, and I think it would requires capturing some of that to be able to make more concrete empirical predictions is my hunch. So basically trying to take theory closer to what's happening in practice. And I think, yeah, that's kind of what has been motivating my research goals. But I think that has potential in saying more about empirical phenomena down the line.
Thank you very much, Nikunj, for this exciting talk. Next week, we'll have a talk by Maria Bongstad. She'll talk about variational inference. And the week after that, we have Professor Thomas Virtanen from Tampere University in Finland. We'll speak about sound event detection. So welcome back. And again, thank you, Nikunj, for today's excellent talk.
Yeah, thank you, Olaf, for inviting me for this. And thank you, everyone, for attending and asking insightful questions. Yeah, that really helps. Have a good afternoon or evening, everyone.
You too. Have a good continuation of the morning.
Yeah.